This section provides a brief introduction to receiver operating curves. It also provides SQL code for constructing these curves. The area under the receiving operating curve is used to test the predictive accuracy of models. This brief presentation was organized by Dr. Alemi. The accuracy of a predictive model is reported by repeatedly examining its sensitivity and specificity at various cutoff levels. Think through a contingency table. On the left side is the true condition that we want to predict. It is either present or absent. When present, we call it positive, and when absent, we call it negative. On top is the posterior odds of the predictions. The number is determined by the predictive model that we are using. When the odds are above a particular cutoff, then we predict that the condition is present. When the odds are below or equal to the cutoff, then we predict that the condition is absent. True positives refers to times that the model predicts the event and it has happened. The model predicts that the condition will occur, and in truth, the condition actually did occur. This count tells us how many times we are accurate in predicting the condition. True negative refers to the number of times the condition is absent, and we correctly predict that it was absent. The negative here refers to the absence of the condition and not errors in prediction. The higher the true negatives, the more accurate we are in predicting absence of the condition. False negative refers to errors in predicting the absence of the condition. False refers to errors in prediction, and negative refers to the absence of the condition. False positive refers to errors in predicting the condition. It is called false because it is erroneous prediction. It is called positive because the error occurs when the condition is present. A sensitive index has a high probability of detecting the condition. It is calculated as the proportion of true positive conditions that are correctly detected by the predictive model. The higher the sensitivity, the more accurate we are in predicting the presence of the condition. A specific index has a high probability of predicting situations where the condition is absent. The specificity is the portion of the patients correctly classified among those who do not have the condition. The higher the specificity, the more accurate we are in predicting the absence of the condition. Thus, sensitivity is accuracy in predicting the condition of what we want to actually predict. High sensitivity means that we detect the condition when it's present. Specificity is accuracy in predicting the opposite, patients who do not have the condition. High specificity means that we do not often mistake other things for the condition. Let us try to calculate sensitivity and specificity for a model that is predicting patients' prognosis. If we are predicting whether the patient lives 6 months, then the true condition is status of the patient at end of 6 months. The posterior odds for being alive is calculated through the predictive model. If these odds exceed a cutoff constant, then we will predict the patient will live 6 months, and otherwise we will predict he will die within 6 months. The true positives is the count of patients we predict to live that who in fact do live. True negative is counts of patients who we predict will die who in fact do die. Sensitivity is a portion of alive patients we accurately predict. Specificity is the portion of the dead patients we accurately predict. This table gives us the predicted probability of death in 6 months at different intervals. We can calculate the sensitivity and the specificity of the predictions at different cutoff levels using this table. Take a look at the table. You see several columns. Each column shows the predicted probability as of death, and on the left side we see how many are alive and how many are dead, and inside the cells we see the actual count of patients. For example, if we select a cutoff level of 0.4, then probabilities below this are predicted to live, and probabilities above it are predicted to die. Probability levels below 0.4 are shown in yellow, and above the cutoff of 0.4, the probability levels are shown in blue. There are 33 plus 6, or a total of 39 persons who are predicted to live who actually do live. These 39 people were correctly predicted from a total of 58 patients. This specificity, that is the portion of alive patients correctly predicted at this cutoff level, is 39 divided by 58, or 0.67. There are also 2 plus 11 plus 33, or a total of 46 patients who are predicted to die who actually do die. These 46 people were correctly predicted from a total of 51 patients. The sensitivity, that is the proportion of the dead patients correctly predicted at this cutoff level, was 46 divided by 51, or 0.90. Note that the calculation of the sensitivity and the specificity depends on the cutoff value. It also depends on what we call alive and what we call dead, so you can always switch things around. But let's take a look at these cutoff values and where they come from. For any index, the sensitivity and the specificity of the index depends on the cutoff point at which we predict the patient will live or die. The column in yellow shows the calculation at the cutoff point 4. We could also calculate sensitivity and specificity at different cutoff levels. Different cutoff points produce different levels of sensitivity and specificity. At cutoff of 1, we would predict that all patients will live, in which case we would have a specific index, but not a very sensitive one. We would predict everyone who lived accurately, but none of the patients who died. If we set the cutoff to 0, then all patients would be predicted to die. We would be perfectly accurate in predicting dead patients, but terribly inaccurate in predicting alive patients. Our specificity will be 0, and our sensitivity will be 1. The receiver operating curve plots sensitivity and specificity at different cutoff points. It helps us get a sense of overall accuracy of the predictions. In order to understand changes in specificity and sensitivity, we draw a receiver operating curve. In this curve, sensitivity is on the y-axis and 1 minus specificity is on the x-axis. The receiver operating curve plots sensitivity and 1 minus specificity at different cutoff points. We show the cutoff points so that you can see how changes in cutoff points leads to different levels of sensitivity and specificity. For example, the cutoff point greater than 0.4 is 1 point on the receiver operating curve. The straight line shows what happens if we predict randomly. The difference of area under the receiver operating curve and the random number shows how much the sensitivity and specificity of the predictive model is better than the prediction of a random number. A random prediction has an area of 0.5. A perfect prediction has an area under the receiver operating curve of 1. The extent to which the operating curve is higher than 0.5 shows how accurate the predictive model is. Let us try to calculate sensitivity and specificity using SQL. We present a code that calculates sensitivity and specificity in 3 steps. First, we select a range of cutoff values we want to try. Then, we compare the predictions to the cutoff value. And last, in the third step, we calculate the actual sensitivity and specificity. In the first step, we generate a set of cutoff values ranging from 0 to 1. Here we show 7 cutoff values, but in practice, many more cutoff values are considered, specifically near 1 and near 0. Another, and in our view, a preferred approach, is to set the cutoff values as the average of every 2 consecutive predictions. First, we order the data in terms of predicted value and calculate a row number for each value. Then we join ordered data to itself and select 2 adjacent rows of data. We then calculate the average of 2 adjacent values as the new cutoff. Finally, we set 0 and 1 cutoff values so that we have a comprehensive set of cutoffs. So far we have shown you how to do the cutoffs. Now, in step 2, we compare the predicted posterior probability to the cutoff value. Any value above the cutoff is assigned a 1, and other values are assigned 0. If we have calculated posterior odds, we need to first convert the odds to posterior probability before comparing to cutoff values. In step 3, we calculate the sensitivity and specificity. Sensitivity is calculated as true positives divided by the number with the condition. True positives is the number where both the actual and predicted fields are set to 1. This is calculated as product of the predicted and actual fields. The product is only 1 when both are 1. The specificity is calculated as the ratio of true negatives to total numbers where the condition is absent. True negatives is calculated as number of cases where neither predicted or actual are 1. Operationally, this is calculated as the product of 1 minus predicted times 1 minus the actual. This product is only 1 when neither predicted or actual are 1. We can also use SQL to calculate area under the receiving curve. Since the area under the receiving curve indicates the accuracy of prediction, we need a method to calculate this area. The area can be calculated in R or other statistical software, but it's best if we can also use SQL to make these calculations. We approximate the curve as a series of adjacent trapezoids. The top of the trapezoids approximates the curve line. The area under the curve is the sum of the areas of the trapezoids. Let us look at one of these trapezoids. The base of the trapezoid is the x-axis. The length of the base is the difference of the values of the 2 points on x-axis and is referred to as run. The height of the trapezoid is uneven and corresponds to the height of each point on the y-axis. The difference in the 2 heights is referred to as rise. The area of the trapezoid consists of two elements, a triangle on top with an area calculated as rise times half of run. In addition, we need to calculate the area in the rectangular area, which has the area of run times the minimum height of the trapezoid. For example, between the two cutoff points greater than 0.2 and greater than 0.4, the triangle has the rise in sensitivity of 0.04 and a run of 0.1. The rectangle below the triangle has a run of 0.1 and a height of 0.9. 0.9 corresponds to the minimum of sensitivity at these 2 points. The net triangle and rectangle areas are 0.004 and 0.09 for a total area of 0.10. When we do this across all cutoff points, the area under the receiving curve is 0.89, which is relatively large and close to the maximum of 0.1, the maximum of 1. This SQL code calculates the area within each trapezoid and sums these areas to calculate the area under the receiving operating curve. This code takes the sensitivity and the specificity of adjacent columns of data. We are joining the ordered table of calculated sensitivity and specificity with itself and telling the computer to make sure to select the next row in the data. This method of joining assumes that the data are ordered by the cutoff values. Next, we calculate the area for each trapezoid by calculating the rectangle and the triangle portion of the area. The rectangle area is calculated as the minimum of the sensitivity values times the run. The triangle area is calculated as half of the rise times the run. In the final step, all the trapezoid areas are summed to obtain the total area under the curve. This set of slides have shown you that the area under the receiving operating curve can be measured and it represents the accuracy of models' predictions.